Hello, and how are you? My name is Muhindo Mubarak, and I'm with my colleague Joshua Vyaruhanga. We are going to present our concept of leveraging artificial intelligence for continuous early diagnosis and detection of malaria in Uganda. So, we're going to basically use the following techniques: uh, an integrated framework using a federated few short learning, feature augmentation, and continuous learning. So let's get started and look at our presentation today. So the introduction and motivation for this concept is Uganda faces significant public health challenges due to malaria. So early and accurate diagnosis is critical for effective treatment, and traditional centralized deep learning approaches require large data sets, and it always compromise the patient's privacy. So our vision is to create a decentralized artificial intelligence model or framework that can adopt quickly and continuously learn and safeguards patient data. So if we are not going to have a main very big data warehouse, we're going to have our model. Our model will be distributed different areas on users' phones or desktops, and then those local models on those gadgets of the users will be learning using the few data that will be collected on those phones, and then they'll be sending what they've learned into the centralized model. And then once we learn, then we can be sending back the updated model that is much more informative and continuously learning. So that's our motivation compared to what's existing at this moment. So the problem is how can we achieve early malaria diagnosis using the limited and localized data while preserving patients' privacy. So here other most important thing is we don't want to be collecting too much patients' information and put it on a centralized database. The patient's information will be remaining on their respective phones, on their respective storages, and then for us shall be only collecting a model that has learned from those local machines without messing with their what, or without tampering their what with their privacy, since you're going to not collect their data and send them to a centralized server. So the objective is to enable decentralized training through federated few short learning and enhance diagnostic precision with federated feature augmentation. Also to implement the continuous learning to update the model in real time. So the related work that we have so far looked at that's available is in federated learning. There is decentralized training for privacy preservation. You can find this work by searching McMahon et al. In 2017. You'll see development about all the work about this federated learning. So we borrowed some ideas from there and how we can improve. We shall explain how, and also the meta learning or the rapid adaptation with few data samples, which is also another work that was published on Fin et al. In 2017, and also continuous learning, a model improvement over time in dynamic environment in Paris et al. In 2019. So here, these are all different techniques that we're going to merge together to come up with something that we think is going to be noble. Uh, and here is the gap that we realized, that most of these approaches, they rely on centralized data, and our framework that we are proposing will integrate the continuous adaptation with federated context. So it will be learning from few data that is on a local phone or a local gadget of a user, and then it sends that data to the centralized model. That is what is that's what is unique with our model that we are proposing. So our proposed model will be in this way. We shall have three core concepts, okay? And that is federated few short learning, which is a rapid adaptation with few annotated samples. So this technology, or this technique has ability to learn from few data. Let's say that you take only 10 images of patients' blood samples or blood smears a day. So by the use of this model of few short learning, it can be able to learn and get important information from those 10 photos that you have taken per day, and then to be able to send the learned model with that few information. So compared to sending the images to the server, shall only be sending only the learned model that has managed to learn from that few data from that particular phone. And when this data will be central, when this model results will be centralized on the central database or the central server, we can be able to come up with something that's much more huge and more informed, that does not pick the data, does not store data or does not collect data from the patient's phone or from the user's phones. And then we shall also, another concept here that we're going to base on is federated feature argumentation. This is a robust global feature representation via CNNs and continuous learning in real time. Real-time model updates as a new data arrives. So it's not going to be static, it will be continuously learning. And you can look at the diagram that you have drawn, that these will be different clients or different users that will be using our model. So when they use the model, for us we use the pictures to learn, and then also update the centralized server, and then also send back the updated server, and the updated model to everyone. And then with time, our model can become much more smart, and does not store people's data. So here is the concept on we also have three main formulas. This is the first one of a federated few-shot learning for the local for the local model that will be on the user's phone. So the local clinics or the local medicians, they'll adapt a global model using only few annotated sample, and the inner loop will update in this formula, whereby the theta is the global model and the alpha is the learning rate, and the L is the support, and is the and L is the support, and the loss of the local support set. So that is the formula. You can look at it clearly, and the explanation of each symbol is bottom there. So that is the formula for the learning model that will be on the user's phone, on the user's gadget. And then you have the federated few short learning. The federated feature argumentation. It extracts, the concept will be to extract robust feature from blood smear images using the CNNs on each client. And the feature aggregation equation will be as follows. And each feature of FI is weighed by the number of the samples and aggregation from the global representation, and it will be summing them up. And here the benefit is it will have the enhanced diagnostics precision through improved feature presentation. And then we shall end up with the last concept, or the last formula, which is the continuous learning mechanism. The system will continuously update as few data is acquired, and keeping the model current. And this is the formula to be using, whereby Y is the learning rate for the new model. And then the periodic aggregation will be that new updates are integrated into the global model to ensure that is sustained and achieves the performance. So the implementation plan for our model is we already have the data set of thick blood smears. We have already shared the details about this data set of blood cells that are infected with malaria and those that are not infected in the in our concept paper. And this data set we collected them from from LHNBC. And this will be the main data set that we shall begin with to come up with the very first original version of our model. And then the processing steps will be noise reduction and construct enhancement using the OpenCV library. Then we shall use the data argumentation and partitioning into support and query sets for the few short training. And then the outcome will be the prepared data for the effective decentralized training model. And then the implementation will be, and for our model development will be the modules. Here are the core modules where we shall have the federated few short learning module, which we can abbreviate as MAML, which will be inspired by the framework in the TensorFlow. So shall use the library of TensorFlow. And then the federated feature argumentation module, which are the CNN based on the feature extractor, and also continuous learning module, which will be incremental and updates with the new data. And then we shall use the backend and the mobile application, whereby the Django REST API or REST API or the Django framework will be used for managing the models. That will be the user interface for the web that will be used to manage the model. And also we shall have the Flutter mobile application that will be on the user's device, and here we'll be using the TensorFlow Lite for training a model on the local machine of the user, or the local phone, or the mobile phone. And then here we designed a photo that is inspiring our work, and expected outcome and significance will be the high diagnostic accuracy despite the limited data, and also privacy preserving decentralization training and continuous improvement via real-time updates. And then significance our significance will be transformative potential for malaria diagnosis in a resource-constrained setting like Uganda. And then the core noble value of our model of our work will be to enhance public health and saving lives in Uganda. Thank you for listening in, and here's the conclusion. So our future work will be the trials with local healthcare providers and refinement of continuous learning mechanism and extension of other medical imaging applications. I thank you so much for having listened up to this point. My colleague will go ahead and present the EDA of our data sets that we already have. Thank you.
Good morning, colleague. My name is Joshua Biaruhanga. I'm here with my colleague, Hindom Baraka. We are here to demonstrate the concept of federated learning. Federated learning is a way by which multiple devices or computers work together to train a machine learning model without having to share their raw data. So instead of sending all the data to the central server, each device trains the model on its own local data and then sends only the updated model to the central server. And then the server then combines this update to improve the overall model performance, then sends it back to the individual update. This approach is useful for privacy, efficiency. It helps improve privacy, since the data is never shared with the central server. So we are going to train a machine learning model that will predict presence of malaria within the thick blood smear. So allow us to walk you through the process. The first step here, we are loading the libraries that we are going to use within our model. So these are the paths where the sick blood smears are located. We have a path for affected blood smear, sick blood smears, then a path for unaffected sick blood smears. So the next is the function that will load respective images. So this function here, we are resizing the images, that is to achieve uniformities, to avoid bias within the model, because if some images are larger than the other, then the model will tend to be biased on a particular image. Then this second function, we are loading the images. You realize that our images are in different subfolders. So this function here will walk through each subfolders and retrieves all the images. So after the images have been loaded, we visualize them. So this is how the images looks like. And then after which we have to concatenating, that is merging both the infected and infected sick blood smear. So we have to combine them. Then also we label them, that is the affected one will be given a label of 1 and the uninfected one will be given a label of 0. Then shuffling, this involves mixing, randomly mixing the samples. The aim is to avoid bias within the model. So if these images are not randomly mixed up, the model may tend to be biased, and the biasness will result into overfitting. So that's the major reason for shuffling of the images. Then here we proceeded to train our model. Splitting, I beg your pardon, that is splitting the data into X-train, X-test, and then Y-train and Y-test. Then we also did, we have a sample for validation, that is X-val, X-test, Y-val, then Y-test. Then we shall also split our data for federated learning purpose. Here we are going to simulate the 3 different regions or 3 clients. So take an instance, we have a team in Mbarara, we have a team in Gulu, we have a team in Hoima, and then our central server will be, say, in Kampala. So these 3 different teams are going to train their individual models. Then after they've trained each model, they will send only the updates to the central server that exists at Kampala. Then here we are defining our CNN model. So after we've defined our CNN model, we go ahead and extract the features within our data sets. And from the graphs, from the above graph, you can see that we effectively separated the affected sick blood smears from the unaffected ones. So the 1 represents the affected blood smear, and then 0 represents unaffected ones. So here we are setting up the 3 clients, that is Hoima, Gulu, and Imbarara. So these are the 3 clients that have been set up. So these clients, once we start training the model, the simulated these 3 clients will run independently. So we shall achieve this using threading. So each after running, they will be able to send updates to the central server. So once they send an update, they get a response. So this is our server which is running. So once it gets an update, it will get an update from each of the different teams, that is Hoima, Gulu, and Imbarara. So that is what we did for this week. We shall continue with the next step of having this model fine-tuned such that we have accurate results. Thank you. That's all from us.